Hello everybody, let's talk about indeterminate forms and another rule that we have for evaluating limits called L'Hopital's rule for examining those limits. The first question is we need to remind ourselves, what was it that made a fraction indeterminate? Well, we had stated that a fraction is called indeterminate when it produces a value of 0 over 0 or infinity over infinity the last time that we discussed this. Now, in this case, the word indeterminate indicates that no single value can be reached. Why? Well, to understand for a fraction, anyways, we need to go back to our definition of, of division. If you recall, a number A, when divided by a number B, produces a number C if and only if A is equal to B times C in the set of real numbers. So, for example, if we took a number like 12 and divided it by 3, we know we would get 4 simply because 12 is the result of multiplying 4 times 3. Now, if we start throwing 0 into our fractions, we run into some issues. 0 in the numerator of a fraction, if I said 0 over 3 equals 0, well, yeah, that makes perfect sense because 0 is the product of 0 times 3. But what if I said, and if, of course, if I say 3 over 0, we simply say that's undefined. The reason why we say undefined and not indeterminate in this case is that having a fraction over 0, there's nothing that would work, right? I mean, if the 3 over 0 is equal to something, then it would have to imply that 3 is equal to some number times 0. So, of course, in our original rule, we try to eliminate that factor. But what if we did something like 0 over 0? Is there a number that makes that true? Well, yes, because 0 would equal to some number c times 0. And that number c, that could be anything. Make it 100, it's true. Make it 0.1, it's true. Make it 17.397, it doesn't matter. 0 times that number is always 0. So we call this value indeterminate. Similarly, by the way, we hadn't talked about this idea that if we take infinity and divide it by infinity to get some number, well, that's also true because infinity mathematically would be c times infinity because it doesn't really matter what c we multiply by infinity. Infinity is really more of a, say, like saying increases without bound. Right? So increases without bound equals c times increases without bound. Well, yeah, that's true. It doesn't matter what value real number c you choose. So we also call this one indeterminate. Now, there are a few other indeterminate values. We can look at those separately eventually, but we can say that, for example, if we took infinity minus infinity, what do we get? Well, that's not a really clear concept because our regular mathematical concepts of subtraction and multiplication, division all sort of break down with infinity, so that doesn't work. 0 to the 0 is also considered indeterminate. 1 to the infinity, well, typically we say that's always equal to 1, but 1 to the infinity is considered possibly indeterminate, right? What could we say about that? How about infinity to the 0? Or infinity to the infinity? What do we do with those, right? So we could consider all these forms indeterminate. We're going to concentrate on these ones, though, right? Our fractional indeterminates, and let's see what happens if we have to deal with those in a limit. Now, you'll recall that in calculus, sometimes when we make a substitution directly into the expression and try to evaluate it by taking the limit by substitution, we will get that indeterminate value. Letting x approach pi from the right and really from the left, in this first case, produces the sine of pi and pi minus pi. And what values do we get? Well, a quick check shows us that taking the sign of the value pi gives us 0, and pi minus pi gives us 0, so that's an indeterminate value. And the similar idea right here, if we take a limit as x approaches 1 of this quantity, we similarly get 0 over 0. Now these are also the same kind of expressions down here in our examples. But in earlier methods, one way of evaluating these, let us recall, was to simply algebraically rewrite the expression. For example, in this first case where I'm taking the limit as x approaches 0 of e to the 2x minus e to the first, wanted to write e as I was talking there, factors, right? That's e to the x minus 1 times e to the x plus 1, and we're dividing by e to the x minus 1, and since that's a common factor, and we don't really care what happens at x equals 0, just as long as we're looking at the behavior as x approaches 0, the behavior of the function e to the x plus 1 as x approaches 0 will be exactly the same as the behavior of e to the 2x minus 1 over e to the x minus 1. And so if we evaluate this by substitution, we find that we get, that's a plus 1, pardon me, we now find that if we get e to the 0 plus 1, we get 2 as a result. So that's relatively easy to evaluate. Another quick example right here of this sort of method is that if we have a limit as x goes to infinity, right? This was one where we had to use a special kind of expression right here algebraically. The way that I had demonstrated this was to treat this as the square root of 1 over x squared. And of course, this is also 1 over x squared, right? We want to make sure that we're consistent. But when I do that, and I take my limit as x goes to infinity right here, I'm looking for a way to get something like 1 over x to the something, which is going to give me 0 as x goes to infinity. So what do I get right here? Well, in the numerator, I'll have x plus 1 times 1 over the absolute value of x. In the denominator, I can multiply in this square root. So I'm taking x squared plus 1 times 1 over x squared. And of course, what happens is that since x is going towards positive infinity, this absolute value of x, the absolute value doesn't really matter in this case. If we were heading towards negative infinity, it might change a sign. But in this case, as we let x go to infinity, x times 1 over a positive value of x is just 1, plus 1 over x. And to the right over here, my denominator becomes 1 plus 1 over x squared. And we'll note that with those 1 over x and 1 over x squared terms, we get 0. So we're going to get 1 plus 0 over the square root of 1 plus 0. Well, this limit is going to 1. All right, well, this was what we have been doing so far. So what is this LHopitals rule? Next video will tell.